Electricity transmission and distribution.
Mom, where does the electricity for my video game come from?
That's a great question. The electricity we use is delivered to us by PSEG Long Island. It comes from far away and from different kinds of power plants. For example, power plants can use coal, natural gas, or oil to make steam. Some plants use nuclear power. There are also natural sources of power from dams, hydroelectric plants, solar arrays, and wind turbines. The plants use these power sources to turn a generator that has huge magnets and wire coils inside. The magnets begin moving, generating currents of electricity in the wire. Usually, power plants have several generators running at the same time that produce a lot of power. The power is transmitted at high voltage and then distributed at low voltage so that we can use it in the house. Transformers are used to raise the voltages 69,000 or 138,000 volts, which allows for more efficient transmission to substations miles away or into a network that connects to other power companies, so electricity can be shared efficiently. High voltages are dangerous, so power companies put the high voltage wires up high on transmission towers to get the electricity to a substation. There, it can be converted to about 13,000 volts for distribution to our neighborhood. At this point, the power is still high up on the utility poles to keep it away from people. To use it in our house, there's a transformer on the pole that converts the 13,000 volts to 120 volts. That travels through the wires to the house, then to switches and outlets in the wall. It's dangerous, though, so we all have to be careful. Electricity is invisible, so you can never tell if a wire is energized just by looking at it. If you ever see a fallen wire, don't go near it. Get an adult or call 1-800-490-0075 to report it. Electricity is used for all kinds of things. Your video games, for charging your tablet or phone, the television, the lights, and almost all of our appliances. It may seem complicated because there are a lot of steps involved in getting electricity to us. I had a few courses in electrical engineering when I went to college. It was really interesting. How about we check out PSEG Long Island's website, www.psegliny.com, to see if we can learn a little more about how they deliver electricity to us.
Electric power generated at a power plant is stepped up to higher voltages by a step-up transformer and then transmitted with use of cables at high voltages to substations. Here, electric power is then stepped down by a step-down transformer and distributed to homes for use. Power loss is minimized by stepping up voltages of electric power before transmission and by using highly insulated transmission cables. Regional control and switching centers in electricity transmission and distribution act as nerve centers of electricity transmission and distribution, ensuring that power is delivered reliably, efficiently, and safely to consumers. Electric power is usually measured in megawatts at power stations and in kilowatts at consumer units. The network of cables, which are mostly carried overhead on metal pylons, concrete and wooden poles, is known as the national grid. Advantages of using alternating current in commercial electricity supplies. Efficient long-distance transmission. SC can be transmitted over long distances with minimal power loss. Easy voltage transformation. Transformers can set up or step down voltage efficiently. Cost effective. SC generation and transmission are more economical than DC systems. Lower energy loss. High voltage SC transmission reduces resistive losses. Easier generation. SC is easily produced by generators, alternators, compared to DC. Safer switching and control. SC can be controlled and switched off more safely than DC. standard for commercial use. Most industrial and household appliances are designed for AC, compatible with motors. AC powers induction motors, which are widely used in industries. Flexible distribution. AC networks can efficiently distribute power to various locations. Reliable and stable supply. AC power systems are designed to handle fluctuations and maintain consistent supply. Dangers associated with high voltage power lines. Electrocution. Direct contact or close proximity can cause fatal electric shocks. Fire hazards. Sparks from damaged lines can ignite fires, especially in dry areas. Electromagnetic radiation. Prolonged exposure may have potential health effects. Equipment damage. Power surges can damage electrical appliances and infrastructure. Aircraft and drone hazards. Low-flying aircraft, drones and balloons risk collision. Tree and vegetation risks. Trees growing too close can cause short circuits and fires. Structural hazards. Collapsing power lines due to storms or accidents pose risks to people and property. Interference with communication. High voltage lines can cause signal disruptions for radios and phones. Workplace safety risks. Construction workers, farmers, and technicians face high risks of accidental contact. Stray voltage. Leakage from power lines can electrify nearby objects, posing an unseen hazard.